I'm Gauthier, a bit of a background. I have a PhD on metaspaces and diffractive optics. I worked for Dispelix and Applied Materials in the past, and I joined ATLANT 3D recently to develop their portfolio of application in photonics. And so I like to challenge myself, so I decided also to work on the photonics integrated circuits and to learn a bit more about it. So that's why also I'm trying to develop such kind of application with ATLANT 3D technology. So a couple of words about ATLANT 3D. So ATLANT 3D is a company based in Copenhagen. It's a startup, like a big startup of 40 people now. We are focusing on different markets, so especially research and academics for microelectronics and optics and photonics. So we have different kind of work, but the idea of the company is to be able to do additive manufacturing anywhere, and anywhere implies also space. So that's why we are working on a program with ESA, where we are trying to launch an atomic layer deposition machine inside the ISS. So the problem, as you may know, in this kind of research and fundamental work, so I stole this picture from Wim Bogart on LinkedIn from 2 weeks ago, I think. The main problem in the area of peak, but not only of peak, in photonics and research, when you want to go from a concept and some simulation to a proof of concept, it takes a lot of time. And what we want to propose with our product and our technology is to be able to reduce that amount of time and to be capable of doing what we call fast prototyping. And that's what we recently introduced, so I will show you at the end of my talk a couple of testimonials, but that's exactly what we started to introduce with our first product, which is the NF Lite, which is a product which allows people who have a clean room or do not have a clean room to be able to do their own deposition of different materials and try to shortcut patterning and time to request and all of the stuff. So how does that work? Maybe you are not familiar with atomic layer deposition, but most of the time atomic layer deposition works with, in general it works with gas, and you will send like a precursor and a reactant inside the big chamber, and by doing some cycles, so different pulse of cycle, you will be able to form layer by layer of your material. At ATLANT 3D, we don't do that. We use what we call a micro nozzle, as you can see on the video. And this micro nozzle is designed by ourselves. It's where we are good at. And we can design like this micro nozzle in order to create kind of a micro chamber, which will allow us to do what we call local deposition. And so why it is great? Because mainly you deposit only where you want to deposit. You do not need to spread the entire wafer. And also it's much more faster because you are much more small. Yes, and so the other great advantage of it, it's like you don't have to have a clean room. You can put the the machine inside the clean room, but you don't have to. And so this is why our first customer, for example, is absolutely not using a clean room, is doing material development, and so he just needs like a really easy tool to create his material. So many advantages of that processes. So ALD is really well known. Like you have many companies working on ALD, such as Applied Materials with Picosun, Benec, and more and more. And so you have a lot of materials and a huge broad portfolio of material. With our approach, we can control the microstructure and the nanostructure of the particle. And so this is one example we really use, so not in photonics, but for example in material development, where people need nanoporous material. Something which is great in photonics, and this is something I would like to start to work on, and I started to discuss with the PIC community, it's we can do conformal deposition. So mainly we can come on top of 2.5 or 3D structure, and we can do a local coding on top of it. And so something I forgot to mention, which is important, it's our equipment is compatible with multi-material switching, which means that you can load the equipment with 2, 3, 4 material, depending on how many number of line gases you have, and you don't have to, switch material. It does automatically. So you can do optical coding, anti-reflective coding, or you can design some optical stack to increase the optical response of your components. Another thing which is great with the approach of the micro nozzle is the fact that you can do gradients of different geometry. So I have a sample on the booth, so if you want I can show you. But with the design of the micro nozzle, you will be able to do height variation at the same time when you do the deposition. Another thing which is great, which I already told you just before, is the multi-material stack. So you can pretty much think about doing a 3D printing of different material directly on top of your component. So this is an example of the different gradients you can do with different. And so this is really great. Like a lot of people do not see it like this in the photonics community, but a lot of people see it in material development. Like here, to acquire all of those data points, it's really fast. Like it takes only one afternoon and you can do your optical characterization and you have directly the property of your material. And so this is an example of different structure we can do with our gradient. And so this is really great if you want to think about different optical cavity or different optical responses. Yes, so one example of application where we did a wafer with multi devices, multi-sensor with the same machine. You can do some crosstalk like this. We have some people working on capacitors where you can directly study the junction of different material. And as I was saying just before, if you want to study, let's say, the optical property of a material, so here it was TiO2. We took TiO2 because it's one of the well-known material in the ALD. You get 50 data points in less than 5 hours, and so after you just do the ellipsometry and you are done. You have the refractive index and you know everything about your material. So now one example of application. So we did this work with the Silicon Austria lab, and so the main problem they had, so I guess, they did not tell me, but I guess, it's that they bought some main mirror, and the problem they had is that they needed a TiO2 coating everywhere except on those red patches. So except of going back to the supplier or people making the MEMS and saying you need to change all the process step and to include a TiO2 deposition, we came and we deposited TiO2 everywhere except on those patches, and it works perfectly for them. So it was really nice in terms of really fast prototyping. You directly take an existing component, you increase the property, and you are done. Other different kind of applications, so where we are showing that you can integrate this process to many process flow. So here it was to study the nanostructure and the porosity of electrodes. Here we have shown results who will be public soon, where we can do electrolysis plating, for solar cell. It's really an interesting work because it works really, really well. So yes, so I will give you a couple of words and some testimonial of our first customer, but this is how I like to sum up the power of that technology. So so this is the University of Vermont. They are developing battery cell with our technology, and this is really great for them because they can study fast the material. Here you see they are telling you you can do precise and localized deposition. You don't need to use huge chamber. And here finally the main, let's say the long-term vision goal of that technology is also to try to remove some process such as the patterning. So to conclude my talk. First, thanks to Jessica and Fabulous for the invitation. But I did not talk a lot about PIC because it's just concept and ideas now. I'm discussing with a couple of researchers. But as I was saying to my colleague just before, I'm happy to discuss if you have some ideas. I started to work with researchers in PICs to do some coding. And my idea is to create a synergy where you send me sample, we, have fun together, we publish some results, and let's start from there. That's all.
Yes, thank you.